Lesson 88. In this lesson, we will continue to look at Maclaurin series and the operations on Maclaurin series, including differentiation, integration, and finding limits. And we will also be exploring binomial series. You should note that in your formula booklet for IB, there are formulas provided to you for Maclaurin series for common functions, such as e to the power of x, ln x, sin x, cos x, and arctan x, I believe. But here we have a more extensive chart taken from a textbook that shows you the interval of convergence of these common functions as well. What I would suggest to you is that you should go back to your IB formula booklet, here it is, and see if you're able to work out the sigma notation of these common functions, okay? Because both versions of these Maclaurin series will become useful in your operations types questions, all right? Let us begin by taking a look at integration and differentiation of Maclaurin series. If I have a function f of x represented as the sum of the terms a sub n times x to the power of n from n equals to 0 to infinity, then its derivative f prime of x can be represented as such as the sum of the derivatives of each term, and the integral of f of x dx can also be looked at as the integral of each term in the series all added up together. Okay. In example 1, we will be looking at the Maclaurin series of cosine x and try to find the Maclaurin series for sine x by using differentiation as well as integration. So let me walk you through this. When we want to come up with the function sine of x from cosine x, I know that the derivative of cos x is equal to negative sine x, which means that I can represent the function sine x as the negative of d cos by dx. But we also know that cosine x can be rewritten in its Maclaurin series form here. And then if I expand this series slightly, its first term when k is equal to 0, I have negative 1 to the power of 0, 1, over 2 times 0, factorial, also 1, times x to the power of 0, 1. So the first term will be 1, and then I can make some adjustments to this series by adding the second, third, fourth term, and so on, still following this rule, but now my k value would be k equals to 1. This series starts from k equals to 1. The reason why we're doing this is that the first term is free of any x's, but I know that starting from the second term, I'm going to have x terms, powers of x. And knowing that the derivative of 1 is 0, this may help me to simplify my work. Okay, and now I can focus on taking the derivative or negative derivative of the rest of the series here. Okay. And then when we are dealing with derivative with respect to x, we know that anything that does not include an x in it is considered as a constant multiple that can be separated from the derivative itself. So this is what happens in the next step. So here first term becomes 0. And then I am taking the derivative of x to the power of 2k, and the rest of the expression remains intact. When I take the derivative of x to the power of 2k, so 2k here is a number, right? We have 2k, the original exponent, multiplied by x to the power of 2k minus 1, which allows me to simplify the very first factor in the factorial, 2k factorial, right? Because 2k and 2k. Continuing, this takes me to 1 less than 2k in the factorial, which is 2k minus 1 factorial. And then there's no change here. If I now let n to represent k minus 1, we do a substitution for any of the k's that we see here as n plus 1. Okay, so let's see what we have got here. So k plus 1 becomes n plus 1 plus 1. So n plus 2. 2k minus 1 is now 2 times n plus 1 minus 1. X to the power of 2k minus 1 becomes 2 times n plus 1 minus 1. And we can simplify this all together into the same expression as you would expect as the Maclaurin series for sine x. Okay. Now, what if we take a different approach? What if I take the integration approach in part B? We also know that when I take the integral of cosine x dx, I get sine x plus c. So it's not identical to sine x, which is what we're looking for, but we can pull a trick here. What if I evaluate a definite integral of cosine x dx, but I can't reuse x, right? Because I want x in my final answer. So I'm going to introduce a dummy variable here, t. So let's call the function cosine t dt, because I know that if I evaluate this definite integral from 0 to x, look at what happens. I'm going to have cosine of t from 0 to x. When I sub in x and 0 into the expression, I will end up getting sine of x. So using this particular relationship, I can now say that sine x is equal to the integral from 0 to x of cosine t dt, but now I replace cosine t with its Maclaurin series representation. Using the rule that we're allowed to just focus on the expression part that has a t in it. So I have the integral of t to the power of 2k dt from 0 to x, and the rest of the sigma notation stays on the outside. Let's evaluate this definite integral. So t to the power of 2k plus 1 over that same exponent 2k plus 1 from 0 to x. So I can now substitute x into the variable t and then substitute 0 into t, which gives me 0, and end up with the following step. So now I notice that the denominator of that definite integral is 2k plus 1, which is exactly 1 higher than 2k factorial. So now I can combine 2k plus 1 times 2k factorial into 2k plus 1 factorial, and then the rest of the Maclaurin series is here. And once again, using a different method, we have found the Maclaurin series for sine x from the Maclaurin series of cosine x. Now let's take a look at other operations on Maclaurin series. In example 2, you're going to use the expanded form of the Maclaurin series of sine x and cosine x to write the terms of the Maclaurin series up to the x to the power of 5 term for cosine 2x minus sine x squared. So you may recall from yesterday's lesson, when we have cosine 2x, it's basically asking you to substitute 2x into the Maclaurin series to replace all the x's, right, in the cosine x Maclaurin series. And then when we have sine x squared, you can do the exact same thing by substituting x squared into the places of x in the sine x Maclaurin series. And because we are interested in all the terms up to x to the power of 5, in your substitution, you will pay attention to what to include and what else you can represent as ... So in the cosine version, I have 1 minus 2x squared over 2 factorial plus 2x to the power 4 over 4 factorial. Because the next term is already an x to the power of 6, I don't have to write it out. For the sine version, I have x squared minus x squared cubed over 3 factorial, which really isn't what I need, right? This is going to be x to the power of 6. So In our final answer, we only need to simplify what we get, and we have 3 terms, okay, plus dot dot dot. Example 3. Find the limit using Maclaurin series of this function x minus arc10 x over x cubed. From your formula booklet, arc10 x is given by x minus x cubed over 3 plus x to the power of 5 over 5 minus x to the power of 7 over 7 plus dot dot dot. So when you're looking for the limit here, you can substitute the first 4 terms of that Maclaurin series into arc10 x, and then simplify x minus x, and then the signs of the other 3 terms shown here, and then divide the series by x cubed. And then once we simplify all the powers of x's, we are really looking for the limit as x approaches 0 of a polynomial function 1 over 3 minus x squared over 5 plus x to the power of 4 over 7, and so on. Any terms that have an x in it, or power of x in it, will become 0 as x approaches 0. So your final answer is 1 over 3. Now let's explore the binomial series. So here we're going to generate the Maclaurin series for 1 plus x to the power of p. So p is a general power. And we know that using the basic Maclaurin series formula, we need to come up with f of 0, f prime of 0, f double prime of 0, up to a certain general term, right? The nth derivative of the function at x equals to 0. And hopefully we can find a pattern so that we can generalize this as the binomial series. So let's take a look. I have f of x equals to 1 plus x to the power of p. So first derivative, p times 1 plus x to the power of p minus 1. Second derivative, we have p minus 1 times 1 plus x to the power of p minus 1 minus 1, so p minus 2 multiplied by p. Third derivative, I can keep p times p minus 1 as so-called coefficients, and then differentiate 1 plus x to the power of p minus 2, so it becomes p minus 2 times 1 plus x to the power of p minus 2 minus 1, which is p minus 3, and so on. I believe you can see a pattern here. Every time we go up one derivative, what do we notice? We notice that 1 plus x has a power of p minus 1, p minus 2, the constant here matches with the nth derivative. And in terms of the multipliers, I have p minus 1, p minus 2. So this keeps going down by 1 as well. And the last term that we have is p minus 2, which is like a number that is just 1 off from the third derivative, okay? So if I generalize this, the nth derivative of the function f of x can be expressed as 1 plus x to the power of p minus n multiplied by p times p minus 1, p minus 2, so on up until p minus n minus 1. What are these when x equals to 0? I have f of 0 equals 1, f prime of 0 is p times 1 plus 0 to the power of p minus 1, so p, and then I have p times p minus 1, and so on, okay? So basically that 1 plus x to the power of p minus n part is gone. So plugging these into the Maclaurin series formula, I'm going to have 1 over 0 factorial x to the power of 0, 1, first term. Second term, f prime of 0, p, over 1 factorial times x. Plus next term, I have f double prime at 0, which is p times p minus 1, over 2 factorial times x squared, and so on and so forth. And then the general term that we will get is p times p minus 1 times p minus 2 dot 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 times p minus n minus 1 over n factorial times x to the power of n plus dot dot dot, because this is an infinite series. I think we are able to write this using a sigma notation. This is the sum of n starting from 0 to infinite of the general term p times p minus 1, p minus 2, times p minus n minus 1 over n factorial times x to the power of n. I don't know how many of you have really, really good memory. Remember Pascal's triangle that we learned in the very first chapter last year? Do you remember we have actually used Pascal's triangle to relate it to the binomial theorem, where you can expand binomials to the power of n? And then we took it further, that we looked at the general form of the binomial theorem, where you have like a negative exponent, or you had a fractional exponent, like x plus 2 to the power of 3 over 2. Right? You kind of memorized two formula that maybe didn't make sense back then. Well, this is actually the most powerful thing that will help you to replace what you have to memorize, because this is the most general form of a binomial series that you can get. And if you look at this p times p minus 1 blah 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 over n factorial business, it may remind you of this choose notation, right? When we see this choose notation, we have p factorial over n factorial times p minus n factorial. So if you have that p minus n factorial, it kind of cancels the rest of that p factorial up here, right? In the binomial coefficients. And now, generally speaking, this p and n can take on values of rational numbers and negative numbers even, okay? So let's practice. Evaluate the binomial coefficient 7, choose 3. Using this formula, it's going to be 7 times 6 times 5. So 3 numbers at the top over 3 factorial. What about B? Now you have 3 over 2, choose 3. What it means is the bottom number indicates you have 3 over 2 times 3 over 2 minus 1 times 3 over 2 minus 2 over 3 factorial. And then you simplify. Very interesting, right? So here we go, binomial expansion. If k is any real number and the absolute value of x is less than 1, because we need to make sure we have a converging series, then the binomial series is given by this formula, p choose n times x to the power of n from 0 to infinity. And notice how this binomial series is 1 plus x. So if this is a different number other than 1, it won't work. And we have to ensure that the absolute value of x is less than 1 to guarantee that we have a converging series. And once we recognize this pattern, we can make use of this formula to, expand the binomial series. So here is example 6. Find the Maclaurin series for f of x equals to 1 over the square root of 4 minus x. So I know that I can rewrite this as 4 minus x to the power of negative 1 over 2. But then if I don't have it in the form of 1 minus something or 1 plus something, I cannot apply that binomial series formula, okay? So let's rewrite f of x as 1 over root 4 times 1 minus x over 4. So I've factored out 4. And then this gives me 1 over root 4, which is 1/2, times 1 minus x over 4 to the power of negative 1 over 2. So if you have to do a comparison between this expression and the formula above, your so-called x is now replaced by negative x over 4. And your so-called p, the exponent, is now negative 1/2, okay? So in sigma notation, you have 1/2 multiplied by the sigma from n equals to 0 to infinity binomial coefficient of negative 1/2 choose n, multiply by negative x over 4 to the power of n. Okay? And now you will carefully work out the terms. Subbing 0 as n. You have negative a half, choose 0, 1, times negative x over 4 to the power of 0, 1. Okay, here we go. N is equal to 1, negative 1 half, choose 1 is always negative 1 half, same as the number above. And then times negative x to the power of, over 4 to the power of 1. Next term, so you have p, negative 1 over 2, times p minus 1 over 2 factorial times the so-called x squared, okay? Well, in the next line, we're going to look for a pattern, okay? So first term is 1. Second term, we can multiply the two negatives, so it's now x over 2 times 4. Third term, I have 1 times 3 times x squared over 2 squared times 2 factorial times 4 squared. I think we're seeing a pattern emerge here, because here you have 2 times 4 times 1 factorial. Here you have 2 squared times 2 factorial times 4 squared. You see how you always have powers of 2 and 4, they match up. And then the top part, you can probably see that you're going to get 1 times 3 and then 5 and so on. So the general term here becomes 1 times 3 times 5 times dot 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 times 2n minus 1 over 2 to the power of n times 4 to the power of n times n factorial in the denominator, and then multiply by x to the power of n. Okay? So we can take this one step further and look at example 7. Sorry, it's handwritten, but in your notes this should be printed. Use the first 3 terms of an appropriate power series to estimate the 4th root of 17 to 4 decimal places. So first, of course, we know that this has something to do with a binomial, and 1 is easy to work with. So let's write it as 16 plus 1 as 17. But we know that if we have 1 plus x, but x is not within the boundary of negative 1 and 1, we will not get a converging series. So in order to make sure we get a converging series, that so-called x part now needs to be between negative 1 and 1. So I have to factor out the 16. Okay? By making my work into this form, the 4th root of 16 is 2. Then I have a binomial of 1 plus 1 over 16 to the power of 1 over 4. Then I can rewrite it using sigma notation. We can now expand the sigma notation, write out the first couple of terms, and then simplify. Okay? So this works out to roughly 2.0305. And if I check on my calculator, the 4th root of 17 is actually 2.030517. So it's actually pretty accurate. Okay?